Hi, welcome to AB Video 3.6a Curve Sketching. This is where we put everything together in order to curve by hand, obviously. Okay, so if you look at page 209, I believe this is page 209, this is what they tell you should be looking at. It's a very long list. Okay, I just want to talk about this really quickly. X-intercepts, if they're easy to find, go for it, because you're replacing y by 0, which means you're solving an actual equation. That could be tough if it's a polynomial of degree 3, 4, 5, etc. Rational functions, fraction equals 0 and the numerator 0, that's pretty straightforward. Y-intercepts are always easy to find, so I would definitely find that. Symmetry, that would be if you really wanted to take the time to check for symmetry. The only thing I could think of is in a polynomial function. If all the exponents are even, then you'd easily know it's symmetric with respect to the y-axis. But and also if it's polynomial function with all odd exponents, it would be symmetric with respect to the origin. Other than that, I don't think I'd bother. Domain, obviously, crucial. Range, I wouldn't bother. Continuity, I don't really think you need to do that. You'll kind of hit on that anyways, because you will find the point discontinuities because you'll factor the numerator and denominator, and notice you have a common factor. You'll find the vertical asymptotes because that's the first thing we'll do, which is what they say below it anyways. And as far as jump discontinuities, that would only be with a piece function. Differentiability, are there any sharp turns? You don't really need to check because the sharp turns will come up when you have concavity, relative extrema. That's how you'll find your sharp turns. Relative extrema, of course, extremely important, the most important thing on these graphs actually, and that you use either the first derivative test, which will always work, or the second derivative test, which works most times. Concavity, of course, you're going to need to find so that you can decide on points of inflection, and also just so that you know the shape of the curve. Horizontal asymptotes, they don't talk about slant asymptotes yet. We'll do that in the next video, and we just did that. And they even tell you what section to find all this in, which is kind of nice. And infinite limits at infinity, that's when the graph, for example, over here goes up forever or down forever at either end. And that's basically rational function and, just end behavior, what happens as you go to the far right, what happens as you go to the far left. So infinite limits at infinity. Okay, so just a little review of the symmetry here. Of course, if all the exponents of x are even, you'll get a symmetric with respect to the y-axis. Point discontinuity, you know how to find. So we just talked about all of this. Here's an example. Vertical asymptote is x equals 2. If you're asked for a justification, which they will do on the AP, you have to either show that the limit as x approaches 2 from the left or from the right does indeed equal infinity or negative infinity. If you want to graph the function, obviously you're going to want to find both, so you have an idea what happens. So on the left it goes down to negative infinity, but on the right it goes up to positive infinity. Something you should know, a graph never crosses its own vertical asymptote. That's never going to happen. However, a graph can cross its own horizontal asymptote. To check and see, what you're going to do is take the original function, replace the y by the horizontal asymptote value, and try to solve the equation. Although most often that equation will have no solution, occasionally you'll get one or more solutions. For example, if the horizontal asymptote is y equals 3, and when you check to see if the graph crosses the horizontal asymptote, you get x equals 5, that means that the graph will cross that horizontal asymptote at 5, 3. Okay? So, here's an example. Horizontal asymptote is y equals 1, right? Degrees are equal, leading coefficient over leading coefficient. So you take your original function, replace the y by 1, and try and solve. In most cases, you'll get empty set, as we said, okay? So, again, just a review, a graph never crosses its vertical asymptote. It can cross the horizontal asymptote. So, what follows are all just examples worked out so you can see what's happening. When you have a rational function, you would always try and factor the numerator and denominator. That's going to help you establish everything. Of course, here, domain x can't equal plus or minus 2. Vertical asymptotes are plus or minus 2. Y-intercept, I think it's easier to plug it in here. If you replace the x's by 0, you'll get negative a quarter. X-intercept, when will this fraction equal 0, right? Because y equals 0 for an x-intercept. Well, that's never going to happen, so there are none. Horizontal asymptote, degree of the top equals degree of the bottom, so it's y equals leading coefficient over leading coefficient. Make sure you give me an equation with a variable equals, not just a number. Right away, does it cross the horizontal asymptote? So you take your original function, replace the y by the horizontal asymptote value, and try and solve. When we try and solve, again, it doesn't. Okay? Now, we're going to try first derivative test. At this point, if you want, I'm assuming you can do the quotient rule. If you want to save time when you're practicing problems, you can certainly use the calculator to find the first derivative. From there, I would not use the calculator to solve. I would hope you could tell that this derivative is 0 when x equals 0, and that this derivative doesn't exist at x equals plus or minus 2. Now, 0 is a critical number because it's in the domain. Plus or minus 2 are not critical numbers because they're not in the domain, but of course we know that they are vertical asymptotes. Now, I factored this x squared minus 4 into x minus 2 times x plus 2 because you need linear factors if you're going to use the alternating sign thing with the exponents. Turns out, of course, that we have a vertical asymptote at 0. We have our vertical asymptotes at x equals plus or minus 2, and we did find a critical number at x equals 0. We know that at x equals 0, we have a horizontal tangent line because that's what made the derivative equal to 0. This is important now because you're going to be graphing. All right? So, if I pick, for example, the number 1 between 0 and 2, I'll get a negative on top, and of course, I'll always get a positive on the bottom. So I get a negative. But the signs do not alternate on either side of 2. 2 comes from this factor. It has an even exponent. However, on either side of 0, here you got your 0 from here, the exponent is odd, so the signs will alternate. And again, on either side of negative 2, because of that square, they will not alternate. So you know the graph is increasing, increasing, decreasing, decreasing. So here, of course, you do have a relative max because the graph goes from increasing to decreasing, and you have a horizontal tangent line there. Now, then you're going to need to find the second derivative for concavity. Again, I'm not going to go through all these steps. You know the quotient rule. Look at how horrendously ugly this is. Oh my God. So definitely use your calculator here. So here's what we get finally for the second derivative. Again, when is that equal to 0? Well, the numerator is never going to equal 0. When does it not exist? At x equals plus or minus 2. Again, those are not crucial numbers because they're not in the domain. They are vertical asymptotes. So the only thing we have to plug in are the actual vertical asymptotes. Again, when you're plugging it into here, the numerator is always going to be positive, right, no matter what you plug in. So it's all going to depend on the denominator. And when you plug in 0 and negative 3 and positive 3, and you could do, again, do x plus 2 cubed, x minus 2 cubed, odd exponents, the signs will alternate. So you get concave up, down, up, and now you put it all together. And this is the part where people mess up. They'll often have all this above information correct, but they don't draw a picture that matches that. So here's our one and only y-intercept. We do not have any x-intercept. Here's our vertical asymptotes. Here's our horizontal asymptote. We know that there's a horizontal tangent line here. We know there's a max here. And we know it's concave down here. Now, on either side of the vertical asymptotes, it's concave up. It can't be down here anywhere because then it would have to cross the horizontal asymptote, and we already checked and it does not. It can't look like this because then it would be concave down, not concave up. Make sense? I hope so. Okay, number 22. This is, of course, a radical equation. It's a cubed root. So the domain is going to be all real numbers. Your y-intercept, replace x by 0. You'll find out it's 2. There's no vertical asymptotes because there's no denominator. There's no horizontal asymptote because, again, there's no denominator. There's nothing to create a horizontal asymptote. For the derivative, again, this is very ugly. I would use your calculator. You find out it equals this. And it will equal 0 when, and then blah, 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 blah. It will equal 0 when x equals 0 or 2. It's not going to exist when x equals 1. Of course, domain's all real numbers, so we have 3 critical numbers and no vertical asymptote. So we have the critical numbers 1, 2, and 0. And again, we do our first derivative test, and we'll find out that, and you can't use the alternating sign here thing because these are rational exponents. So you will have to actually pick a number from each area. interval and plug it in and see. Again, at this point, because we're graphing, I'd write down that you got these when you set the derivative equal to 0, so there's a horizontal tangent line there. But at x equals 1, we got that because that makes it non-existent, so there is not a horizontal tangent line there. So we have a relative max, min, max. Second derivative equals 0 when x is 2, doesn't exist at x equals 1. Oh, sorry, not at x equals 2. It equals 0 when x, never equals 0, it turns out. It doesn't exist at x equals 1, so that's our only crucial number. And it turns out when you plug it into here, it's concave down on both sides. So putting it all together, we have a y-intercept of 0, 2. We have a horizontal asymptote at x equals 0 and again at x equals 2. So those are our two relative max points. We have a relative min point at 1, 0. And notice it's increasing in concave. Here it's increasing concave down, decreasing concave down. There's our does not exist derivative at that point because it's a sharp turn. Increasing concave down, decreasing concave down. Number 20, remember there is a product here. I factored it. The domain, the integrand would have to be bigger than or equal to 0. That's a bit of work because it's a quadratic inequality. You start by solving the quadratic equation and then you do the pick and plug. So it turns out that's the domain. There's no vertical asymptotes. Intercepts, again, plug in x equals 0 to get y equals 0, plug in y equals 0 to get x equals 0, and x equals plus or minus 3, as you can see here. First derivative, I'd use the calculator at this point. It's equal to 0 when x equals plus or minus 3 over root 2. It doesn't exist when x equals plus or minus 3. But you got to keep in mind our domain is from negative 3 to 3. So really at negative 3 and 3 you have endpoints. So you're not going to call them relative mins or maxes because there's nothing on one side. There has to be something on both sides for you to be at the top of the hill. So then we find, so there's our first derivative test. I'm not going to go through all the steps, you know, this is the shtick. We get a relative min and relative max. Here's our second derivative. It's equal to 0 when x equals 0. And when x equals plus or minus, if you solve this equation, 3 point something, that's not in our domain. Doesn't exist when x equals plus or minus 3. That's our endpoint. So we have a number. In each case, by the way, notice we have a number segment because of our restricted domain. And you find out it's concave up and then concave down. And then you put all that together and you have the following graph. Here's your min, your max. We had a point of inflection at 0, 0. It's decreasing concave up, increasing concave up, increasing concave down, decreasing concave down, and there's nothing over here. And that's the end of the video.